Welcome Inti Sodemann on our final lecture of day, and he will present fate of Laughlin states in ideal Chern bands. Thank you.
Hello everyone, can you hear me? Good. Yeah, so first of all, let me begin by thanking the organizers, Subhro and Sergej, for the invitation. It's really great to be here, and also for doing all the hard work of putting together this very nice conference. Yeah, so I will be telling you about some recent work I did with my postdoc, Saranjo Moitra, at the University of Leipzig, trying to understand, the nature of the Laughlin state in some kind of generalization of the lowest Landau level, something that we're going to call an ideal Chern band. And I'll try to define what that means. Yeah, so just a little bit of advertising. I'm at the Institute of Theoretical Physics at the University of Leipzig, just about an hour away by train from Dresden and Berlin. So if you're ever around in the area, please let me know. It would be great to have you come visit us. It's a place with rich history, where Heisenberg used to be a professor and where he trained some of the people who laid out the foundations of solid-state physics. They were his PhD students there in Leipzig. Yeah, so basically this is a summary of the kind of main message that I want to convey in this talk. So we want to try to understand the ideal, the nature of the Laughlin state in some kind of the formed version of the lowest Landau level. Here in this axis is the filling. So we have different Laughlin states at different fillings. And this y-axis is some kind of parametrization of the deformation of the usual lowest Landau level. So think about this line as being the usual lowest Landau level, and everything below here as some deformation, which is this kind of what I will call the ideal Chern band. And I will define, exactly what these parameters are throughout the talk, but just here to give you kind of the key message, okay? So in the usual Landau level, the Laughlin state is in a topologically ordered state, the famous topologically ordered state that we know and love, with fractionally charged excitations, anions. But what we found is that the Laughlin wave function, when you write it in these generalized ideal Chern bands, the same wave function undergoes actually a phase transition into a highly non-trivial state that we're still, in a sense, trying to fully understand. We call it the Laughlin dielectric. It's a kind of gapless state, okay, but a gapless state with very strange characteristics. For example, it does not break spontaneously any symmetry, so there is no symmetry breaking in this transition. And also, very interestingly, this state has power law correlations of local operators that have continuously changing exponents. So it has power law correlations, but the exponents change continuously. Yeah, so let me kind of first begin with some very brief review of some basics of quantum Hall. So if you take, electrons in 2 dimensions and you put them under strong magnetic fields, then the cyclotron radii basically become quantized into different Landau levels. And these Landau levels are highly degenerate. Basically, there is a lot of single particle states in each Landau level, which are roughly speaking associated with where you put the center of the cyclotron orbit. So there's a lot of states. So if you have a sample of some area A under a magnetic field B, the number of states within a given Landau level will be the number of flux quanta that pierce the sample. Okay, so it's a highly degenerate flat Chern band, if you wish, in modern language. And so one very crucial parameter in the description of Landau levels is the filling factor, which is how many electrons you're putting into those single particle states. So it's defined as the number of electrons divided by the number of states in a given Landau level, When this filling factor is an integer, then we get the integer quantum Hall effect with quantized plateaus of the Hall conductivity in integers of these fundamental constants. But when this filling of the Landau level is a fraction, then you get the fractional quantum Hall effect. So for example, the most famous state happens when this filling is 1/3. That's the Laughlin state, the first state that was understood and discovered, where you see a plateau of this Hall conductivity with a fraction of 1/3, okay? But in general, when you have a very clean two-dimensional electron system, as you change the magnetic field, or equivalently the density, which is basically changing the filling of this Landau level, you see a very complex and rich sequence of phase transitions between different states. So it's really a zoo of correlated phases. Each of them is, in a sense, a different topologically ordered state of matter. And so why does the Laughlin state form? What is the key to its energetics? So let's go to this lowest Landau level. Imagine that we're fractionally filling it. If you choose the correct gauge, the single particle wave functions are analytic. They are holomorphic in this coordinate. And so basically all the single particle wave functions in this lowest Landau level can be written as an analytic polynomial of this coordinate. We can take to be some power of the coordinate times some fixed function, which for the lowest Landau level takes this form, exponential of minus z squared over 4L b squared. L is the magnetic length. So all the different single particle states are parameterized by the choice of, holomorphic polynomial that you put here in front of this function. And then when you have many electrons, the many-body wave function is just parameterized by a holomorphic polynomial of n coordinates. So you have n electrons, you have the generalization of this to n coordinates, and this factor is kind of fixed, is rigid, always this product, okay? And so, let's suppose that we look at this wave function from the point of view of electron 1, let's say, of one of the electrons. Let's take electron 1. So there is a theorem, was proven by Haldane a long time ago, that the number of zeros that this function has, from the point of view of any coordinate, so when you're fixing all the other coordinates, just looking at it from the point of view, let's say, of the first coordinate, it's equal to the number of flux quanta. So the number of zeros that the wave function has equals also the number of flux quanta, the number of states. So if we are at some filling like 1/3, and we just pick a random polynomial, what we will have is a picture like this. So this is kind of a cartoon of this wave function viewed from the point of view of the first electron. The red dots are, the coordinates, all the other coordinates that we are holding fixed for the other particles, and the stars are the zeros. If you just choose a random polynomial, you will have a bunch of zeros. So 3 zeros for every particle, basically, but they will be, placed in some kind of random positions. But what makes the Laughlin state special is that it's a state that binds the zeros as close as possible to the particles. So the Laughlin state basically takes each of these zeros and puts them on top of the particles. So this is how the electron sees the wave function in the Laughlin state. And why does it do this? Why is it a good idea to do this? The zeros are the places where the wave function has very little probability to be at. So by binding the zeros to the particles, then this particle has very low probability to be close to any other particle. And in that way, if you have any kind of, generic repulsive Hamiltonian, that will be a very good thing to do to minimize the repulsion. It gives very good correlations for electrons avoiding each other, okay? So, and then you get this kind of unique, by that principle of binding the zeros as close as possible to the particles, you basically get a unique polynomial and fixes basically the wave function. So it's the wave function that binds the zeros best to the particles. These zeros, people sometimes talk about these zeros as fluxes or vortices. They are essentially the same thing. And so this bound state of the zeros or fluxes to the particle is sometimes called the composite boson. And so people say that the Laughlin state, this process of binding the zeros to the particle, people describe it as a condensation of a composite boson. So the Laughlin state can be viewed as a kind of Bose-Einstein condensate of a bound state of the electrons to 3 zeros. Yeah.
Is there this picture the way that people rewrite the Chern ideas? Is there only one effective theory that fits with this condensation? If you imagine
Yeah, the field theory depends on how subtle you want to go. Like people are still arguing about what is the best theory, but I think at some basic level, that's the essence of what the Chern-Simons action is doing, right? It's binding fluxes, is binding these zeros to the particles. Excited states is a very different question, right? So there's all this discussion of is this graviton mode, for example, from Haldane, that graviton is some kind of mode that parameterizes the nematic deformations of this bound state. So the Chern-Simons has essentially no information, all that information about excited states is missing. Yeah. Good. So let's now do something that actually was done by Laughlin himself, which is very powerful, which is so-called the plasma mapping. Okay, so here we have the Laughlin wave function now, slightly generalized by binding m zeros. You can write the Laughlin wave function at filling 1 over m. And so Laughlin noticed that if you take the square of this wave function and you write it as the Boltzmann weight of a classical Stadtmech problem, it has a very simple, beautiful interpretation. So just the square of the wave function, by doing a couple of lines, you can write it as the statistical weight of a classical two-dimensional Coulomb gas. So these zeros basically turn into repulsive interactions in this classical potential. So the electrons look like point-like objects with charge, let's say, -1, repelling with a logarithmic potential. And then this fixed part looks like the potential is a kind of one particle potential that would be generated by a uniform positive charge background. The problem has the same statistical, the same correlations as the classical Stadtmech problem of the one component Coulomb gas with a fixed uniform neutralizing background, a kind of Gillium version of the two-dimensional Coulomb gas. And one crucial point is that this is a problem at finite temperature classically. So the temperature, the inverse temperature, is just parameterizing essentially the exponent of the Laughlin wave function. So the exponent of the Laughlin wave function is up to this factor of 2, which is basically the inverse temperature of this Coulomb gas. And this is a very powerful, mapping. For example, we just discussed that the ground state is this state in which all the zeros are bound to the particles, but you can construct states for quasi-particles in which, for example, you leave 1 zero kind of floating around without binding it to the particle. So if you write down a wave function like this, in which there is an extra zero somewhere that is not bound to the particles, it's just at some given location set a zero, then you can also do a Coulomb gas mapping for this wave function with this extra defect zero, so to say. And what you will find is that this zero acts as a kind of test charge, as if you put a test charge into the Coulomb gas, but with a fractional bare charge, okay, of -1 over m. It's kind of repelling the electrons. But what happens? The nature of this physical quasi-particle depends on what the electrons do around it. The zero is just some kind of artificial theoretical object, right? So what do the electrons do around it is really what characterizes the nature of this defect as a quasi-particle. And so this is very clearly illustrated by understanding what is the nature of the phase diagram of this Coulomb gas. It turns out this Coulomb gas, as a function of this inverse temperature, which is the inverse of the Laughlin power, has a non-trivial phase transition at very small filling factor. So people knew that for a long time, that if you make the Coulomb gas very cold, eventually it will stop from being a plasma, essentially a classical metal in which the charges are just fluctuating a lot, and it will crystallize. It will have a kind of crystallization transition. In order to have the sharp topological properties of the Laughlin state, it is crucial that the wave function lands on this side, on the side in which you are in the plasma. Because this is, for example, what guarantees the fact that this zero has a precisely quantized physical fractional charge. This charge that I mentioned here is just kind of the bare charge that appears in the Coulomb gas, but the physical charge is given by the screening cloud of electrons that forms around this defect. So it's when the plasma has perfect screening, so that the screening cloud exactly cancels the charge of this test charge, is that the physical charge of this quasi-hole is exactly quantized to be 1/m. In this other phase, is not clear. So all the topological properties hinge on the behavior of these wave functions to be, the same as the statistical phase that is the plasma of the Coulomb gas. Okay, so that you get perfect screening. Yeah. Yeah. This is known from numerics. No proof of this. I don't think there is anything rigorous, but there have been some very recent, much more systematic and large-scale numerics that have essentially confirmed that there is a phase transition around that point from Monte Carlo. Yeah. Yeah, that's usually for a different kind of the Coulomb gas, which is the two-component Coulomb gas in which positive and negative charges are both fluctuating. Doing RG for this Coulomb gas is actually very hard because you need to control the RG, you have to go to the dilute limit of the Coulomb gas. This one is never dilute. So this one is can be understood, for example, at filling 1, can be understood exactly because it's a Slater determinant, but at other fillings, which are other temperatures, generally it's just Monte Carlo and numerics. There's various kind of approximate methods, but it's hard to do something controlled, this Coulomb gas. Exactly, it's much harder, yeah. But the fact that this wave function maps to the plasma is crucial to have the topological properties. If it was not the plasma, you would not have the topologically ordered state. So the plasma and the fact that it has perfect screening is what implies that this wave function has short range correlations, is what in the end leads to the existence of a full gap for all the excitations. This is the figure copied from the classic work of Girvin, McDonald, Platzman on the collective modes of the Laughlin state as a function of wave vector, which are completely gapped and which are imply that the state has exponentially decaying correlations. So it's a fully gapped state. All of that relies on being on the plasma side. Okay, so now, as you probably have heard, for Moore-Reedy, kind of, we can talk about it, it's very complicated. There is a kind of mapping, but it's not very good. But almost, Laughlin and Halperin states, but for other states, not clear, yeah. So now there is there has been a discovery of fractional quantum Hall states without magnetic fields in Moroz materials, in particular in molybdenum ditelluride and also in pentalayer graphene. People have observed by now clear signatures of fractional quantum Hall effects, fractional quantum Hall states at zero magnetic field. The theory that has the kind of theories that people have proposed to understand the appearance of these fractional quantum Hall effects is that they are originating from very flat Chern bands that are also nearly ideal. So there has been a lot of interest in understanding, what happens to these fractional quantum Hall effects in these so-called ideal Chern bands, which I'm about to define in the next slide. So this gave us kind of motivation to try to reconsider this question of what is, the nature of the Laughlin state in these generalized Chern bands. All of these beautiful results coming from Moroz materials. And so let me briefly review what is the notion of this ideal Chern band, which is a kind of generalization of the lowest Landau level, okay? Perhaps, the first work that pointed out the importance of some of this inequality between the metric of a block of a band and the Berry curvature was this one by Rahul Roy. But basically, an ideal Chern band can be defined as a band in which this inequality is saturated. So this is the trace of the metric tensor, and this is the Berry curvature locally. So you have a kind of Berry curvature and a metric tensor that are changing as a function of wave vector. But when this inequality is saturated, the band can be called an ideal Chern band. And what I will review here is the so-called real space point of view of these ideal Chern bands. This real space point of view was, essentially kind of discovered almost by accident by studying the flat ideal Chern bands that appeared in the chiral limit of twisted bilayer graphene from Ashbin, Bishbanath, and collaborators. And so what is the real space point of view of this ideal Chern band? So what people have been able to show is that when this inequality is saturated, the wave functions constructed out of these bands are essentially holomorphic functions, just like in the lowest Landau level. So basically, they have this kind of form. So the single particle wave functions can be written as the same kind of holomorphic part that we had before, and the only thing that you need to change is a fixed non-holomorphic part, which is no longer this exponential, but it's something that you have to, solve in a case-by-case situation. It's something that depends on the microscopics of your Chern band and of your material and so on, but it's some fixed function. So once you have a band, this will be some fixed function, and the only thing changing is, parameterizing different states within this band is going to be this holomorphic polynomial. So they are very close to the ones that we have in the lowest Landau level. Exactly. So what I was going to say next is kind of related to what you're mentioning. So actually, one of the first examples of these ideal Chern bands appeared in this classic work of Aharonov and Kasher. So of course, it's not discussed in this language, but it's essentially now we can view it as an ideal Chern band, which is if you take a Dirac fermion in 2 dimensions. You put it in a magnetic field, as we all know, from graphene, there is a 0 Landau level, exactly at 0 energy. And it turns out that if this magnetic field is non-uniform, these 0 energy states stay exactly at 0 energy. They don't change. The 0 Landau level wave functions change, but the energies stay exactly at 0 energy. All the other Landau levels become dispersed. So the 0 energy manifold of Dirac fermions in a non-uniform magnetic field is essentially an ideal Chern band. Okay, so you can write down the wave functions for these Dirac fermions in a non-uniform magnetic field as follows. So the same holomorphic part times the exponential of some function that you need to work out by solving this Laplace equation. So there is a non-uniform magnetic field that acts as a source of this Laplace equation, and once you solve that phi, then you fix it. For a given fixed profile of this magnetic field, this phi will be fixed, and then all the states are parameterized by the choice of this polynomial. So this is kind of one of the simplest models of how to get one of these generalized. If it's uniform, it's just the usual Landau level. So this is just how to deform the usual Landau level into this generalized band. And yeah, so let's write down then the Laughlin wave function generalized to these ideal Chern bands. I will basically take these as my model of ideal Chern bands. I just imagine that we have electrons moving in the 0 Landau level of a Dirac fermion in a non-uniform magnetic field, and I will project the physics to this Landau level, so I will ignore all the other things. So all the wave functions can be parameterized like that. And so we have a Laughlin wave function now in this new Landau level, which has, again, the same kind of holomorphic part time, and the only thing that is changing is this rigid part that we need to work out for any given magnetic field. And so again, we bind the zeros to all the particles as close as possible, the same principle. So we have a generalized Laughlin wave function, and we can still do the same Coulomb gas mapping. So if you take the square of the Laughlin wave function, it can still be written as the Boltzmann weight of some classical statistical mechanics problem. And what we have is essentially that we have electrons, point-like electrons, still, repelling with logarithmic forces, and the only thing that changes is the background potential. So in the usual Landau level, we had this kind of Gillium problem, the potential generated by a uniform charge. Now we have a potential that is going to be spatially dependent, that is generated in the end by this spatially dependent magnetic field. And so we need to understand what happens to the Coulomb gas when we put it in a spatially dependent potential. And the temperature is again the same, so it's 2 times the temperature is the inverse of the power, and the potential behaves as follows, okay? So if you take the magnetic field, so there's some kind of non-uniform magnetic field as a function of space, imagine you integrate it over some region such that its integral equals 1 flux quantum. Then you can show that this region acts as a background charge with fractional positive charge. So it's trying to neutralize the electrons. The electrons we're taking to be negative, let's say, but with charge 1 over m. So every flux quantum carries Coulomb gas charge 1 over m of the background, but it's now non-uniform. It's kind of like a lattice, let's say, for example. So in Moroz potentials, Moroz systems, typically what happens is that the effective flux per unit cell, every unit cell carries 1 effective flux quantum. So the Moroz systems look like systems in which, when you do the Coulomb gas mapping, would look like statistical mechanic problems in which there are ions that carry fractional charge 1 over m per unit cell. So I'm going to kind of, take a little bit of poetic license to modify the problem to make it, as simple as possible. But the idea is that even after we try to make the problem as simple as possible, it will refuse to be trivial, and it will behave in a very non-trivial fashion. So I'm going to take a model in which the unit cell carries m fluxes. So we're looking at the Laughlin wave function with some particular exponent m. I'm going to also kind of engineer the spatially dependent magnetic field so that the unit cell has m fluxes. That means there is 1 electron in average per unit cell, right? And also from the Coulomb gas point of view, each unit cell will have then charge plus 1. Because remember, every flux quantum carries charge 1 over m. So I put m fluxes. So each unit cell is going to carry charge 1. And for concreteness and simplicity, although the main conclusions don't depend on these particular details, we're going to take that the magnetic field is just generated by solenoids. So just imagine a lattice of solenoids of some radius sigma, and inside these solenoids there is finite magnetic field, outside is 0, and the integral inside is such that there are m fluxes, so that the charge is plus 1 of each ion after we do the Coulomb gas mapping. Basically, then what we have is a kind of classical problem of a kind of classical hydrogen crystal. Every solenoid will behave like a proton, kind of spread, the charge spread over the entire radius with charge plus 1, and we have electrons floating around that are itinerant. The protons are kind of fixed. The electrons are, statistically fluctuating, and the question is to understand, the phase diagram of that problem. And so it turns out that, people in the StatMech community studied that problem a while back, and they did even numerics of that particular problem of, Thomson crystal, they call it, sort of like protons in a crystal, and they found this phase diagram, okay? So the x-axis is essentially the temperature of the Coulomb gas multiplied by 2, so it's equal to the filling factor of the quantum Hall problem. And the y-axis is the ratio of the solenoid radius to the distance between solenoids, okay? So when the solenoid radius is kind of large or comparable to the distance, we are back into the usual Landau level limit. And as we change the solenoid radius, we are more and more in this sort of more non-uniform magnetic field problem. And what they found is a phase transition. So when the solenoid radius is large, the electrons are actually unbound. They are fluctuating, they form a plasma, they form a classical metal. But eventually, when the solenoid radius shrinks, the electrons bind to the ions. They neutralize the ions, they form a classical insulator. So every electron is trying to bind to each ion. They carry opposite charges to form a neutral atom, basically, a neutral kind of classical hydrogen. And so this can happen even if you're at filling factor 1/3. Let's say if you take like the classic Laughlin state, and you just start, compressing the magnetic field into these solenoids without changing the filling factor, there will be a phase transition from plasma to dielectric. And the nature of this phase transition is a Kosterlitz-Thouless phase transition. The reason it happens, from statistical mechanics, is basically that the usual Kosterlitz-Thouless argument. So at high temperatures, you're dominated by entropy, so the electrons want to be kind of fluctuating, and in the gas phase, and eventually at low temperatures, you're dominated by energy, and the ions want to form bound states and neutralize, or neutral bound states, okay? Basically, what is happening is a kind of crystallization of composite bosons, when you think about it, because the charges in the Coulomb gas mapping are basically keeping track of what were the zeros of the Laughlin wave function. So the electron still is carrying all the zeros around, all the fluxes, but the bosons are now, crystallizing. They are forming this kind of lattice. But one important point is that in this transition, there is no symmetry breaking. All that is changing in the end, as I'm going to show, are correlation functions. I designed the problem precisely so that the solenoids had, the unit cell in the solenoids has 1 electron per unit cell. So there is no CDW formation. The plasma here has already kind of density modulations, right? Because of the explicit symmetry breaking of the solenoids. And all what happens in this transition is that those modulations kind of increase by a lot. But the two states have the same symmetry. There is no symmetry breaking along this transition, just the binding of the electrons to these solenoids. And so basically, a kind of central quantity that characterizes this dielectric is the dielectric constant. It sort of measures the polarizability of these atoms, okay? In the plasma, the plasma is a metal, so it has infinite dielectric constant. In this phase, this dielectric constant is a non-trivial function of these two parameters of the temperature and this radius. Is hard to compute, but it's just some number. It tells you kind of what is the polarizability of these ions. And what we know for sure is that in the limit of very small radius, this dielectric constant approaches 1. And at the BKT transition, it approaches a universal value, the universal BKT value. And then there is a jump of this dielectric constant to the inverse jumps from finite to infinity, to 0, let's say. Yeah. The BKT RG usually are done for the two-component Coulomb gas. So you need the positive and negative charges to be fluctuating. This is a slightly different problem in which the positive ions are held fixed and only the negative ions are fluctuating. For that, I don't think that you can do all the same tricks that people do of RG. Not as simple. But the physics is very similar at phenomenological level. One of the things that makes this complicated is you cannot go even to grand canonical ensemble because the ion lattice is fixed. You have to work in canonical ensemble to understand this one component Coulomb gas. Yeah, the nature of the transition is very similar, but there are some very important subtle differences that you cannot just copy paste what you have in the two-component Coulomb gas. So this is a very strange state. It's a state that has power law correlations. The plasma has exponentially decaying correlations, but this dielectric will have power law correlations. For example, the density-density correlations decay like a power law, and the exponent is again controlled by this dielectric constant. So what you can say for sure is that this exponent is 2m in the limit of very small radius, and it approaches a universal value at the BKT transition, but knowing exactly this curve is difficult. It takes this form. And the reason why the correlation functions decay like power laws has to do with the probability to ionize these atoms. Basically, when you pull out the electron, the negative particle away from the proton, so to say, the probability to ionize decays like the exponent of a logarithm, and so that gives you power law. So everything becomes power laws, and all correlation functions have power law decaying form. And so this dielectric state, this implies, because the correlation functions decay like power laws, this implies that this state must be gapless. Any fully gapped state of matter should have all correlation functions decaying like exponentials. But because this decays like power laws, this must be a gapless state. But there is no symmetry breaking. So this gaplessness, cannot be coming from usual kind of Goldstone mode point of view. Some kind of gapless state that doesn't break symmetry. One of the things you can do is not exactly RG, but you can do a kind of control expansion at small radius limit, a cluster expansion. For example, to compute the dielectric constant in powers of this sigma over A. Okay, so this is these are non-trivial calculations, so the coefficients are non-trivial, but in principle you can compute in powers of sigma over the distance between the ions, the dielectric constant in this regime. And so, what is this state? We're still kind of really trying to fully understand what is the nature of this phase. It's still not completely clear to us. I am not aware of any fully stable phase of matter in 2 dimensions that has a ground state with continuously changing exponents. But there are some precedents that people have found in the literature of critical states. So states that are, at critical points separating other phases of matter. People have found examples where those can have, continuously changing exponents even in 2 dimensions. So for example, there are several arguments that the RK point, the Rock's archivalson point in the square lattice is kind of the termination of a continuous line of critical points with continuously changing exponents. So it might be possible that this Laughlin dielectric is not a fully stable phase of matter, but it's some kind of critical plane. There is some kind of third axis here that is separating other phases of matter. Maybe. We still don't know. Yeah, this one is believed to have dynamical exponent 2. Yeah, so just to go back a little bit to Moroz, since we did this, important modification where we put the fluxes kind of to have m fluxes per unit cell. In Moroz, we have, only 1 flux per unit cell, so it sort of looks like a Coulomb gas with fractional charge per unit cell. So, a natural possibility then that people need to consider now in studying these Moroz materials is that even if you have the ideal Laughlin wave function being sort of a good approximation to the ground state, it doesn't mean that it's a topologically ordered state. It could secretly be one of these, non-trivial states, and basically in that case, it would have to come like a CDW with true spontaneous symmetry breaking, because you need to kind of enlarge the unit cell so the new unit cell has m fluxes to construct this kind of a state. So there could be a kind of CDW-like version of the state that I discussed in the more kind of natural setting for Moroz materials. But it's also possible that other more non-trivial orders, of course, could arise. Yeah, and so with that, kind of let me summarize. There is this very non-trivial phase of the Laughlin wave function. So just having Laughlin doesn't mean you're topologically ordered. That's the main message, okay, to take home. Laughlin has a lot of life inside. It's not just topological order. Thank you.
Hi.
Yeah.
So, is it possible to do this single mode, construct this quasi-particle type of excitations and try to understand what happens to the energetics of these on top of these wave functions?
Yeah, we tried, but it's hard.
Okay.
Because one of the things that makes it hard is that in the usual, the single mode approximation relies crucially on the algebra of the density operators. That they satisfy this GMP algebra. And that algebra in the ideal Chern band is still closed, but it's a much more complicated algebra. So constructing the whole theory looks much more challenging. We're kind of playing with those things, but I'm not convinced that's the best approach, to just kind of repeat GMP with the same. One needs to, we're still trying to figure it out, but it's not so easy because the algebra of density operators is non-trivial.
Even with creating a single zero?
Say that again?
If you create a single zero and try to ask what is the energy of those kind of states?
The zero, depends on which Hamiltonian you have. So the Laughlin state is the ground state of some ideal Hamiltonian. You can project that same ideal Hamiltonian to this lambda level, and then the zero is always a zero energy state. So the energy is kind of the zero. The harder one is the quasi-electron, the one that has instead of a zero, like a removal of one zero. Yeah.
Yeah, so you took this model of solenoid, which is really nice because we can do something like this. But in terms of the initial Chern band, is there a way to relate this effective sigma to some aspects of the quantum geometry of the band?
Yeah, so actually I don't know like an explicit formula that tells you the real space magnetic field given the momentum Berry curvature. I don't know if there is like a simple formula. In principle, you need to kind of work it out after calculations. But the idea is you have an ideal Chern band, at least in the simplest case, like Chern number 1 and so on. And for any ideal Chern band, there is an effective real space magnetic field. Okay? And the idea, is that it's some kind of function. People have computed it numerically, and it's typically like a smooth function with some high peak. But yeah, it needs to be computed. Yeah.
So in this construction, if you do not have the like symmetry,
the symmetry is not crucial because you see what I was imagining actually didn't mention that is that these solenoids are making a triangular lattice. To copy this phase diagram, the numerics that people did was a triangular lattice. So once you put triangular, there is no symmetry. So you could slightly deform the solenoids into hexagons like. And it would not change.
And then in this case, like it can one get to the nematic phase by the change the form of the plug-in?
The nematic state.
Yeah.
Yeah. So something we're working on is that all of these are sort of got us thinking about the usual Landau level. And I never explained what this dotted line means. Basically, this model of solenoids that people take, at some point the solenoids start overlapping. So it's not a good model anymore, right? And so that's kind of this dotted line where the solenoids start overlapping. I stop looking at the classical StatMech numerics, but I imagine that if you just kind of deform the solenoids until they become, just filling completely uniformly the space, right? This will continuously go to the usual Landau level, right? So this is this dotted line. And so it should eventually go into this critical point that I mentioned at the beginning of the crystallization of this 1/70. But then we started thinking about this state at 1/70, and we realized that actually this state below 1/70 is not just a crystal. Because you have to think about it as a crystal at finite temperature. So you have to apply all this consideration of Halperin-Nelson type theory of crystals in 2 dimensions at finite temperature. And because there is no long range order, actually the crystal is actually destroyed. And so this state is more like it's a kind of nematic state in the end because there is no long-range positional order, but it has long-range orientational order, like this Halperin-Nelson. So anyway, I'm now telling you something that we're kind of working at the moment. This classic state below 1/70 is not even a crystal, but it might be kind of nematic. In a given, the Laughlin wave function in the Landau level should do things in a unique way. So in a sense here, we're asking what is the Laughlin wave function that? Then you could maybe change the Landau level, make it kind of elliptical, then you will deform the question in a sense. Yeah.
More questions? Then
yeah.
You kind of assume that it's a Laughlin state.
Yeah.
Everywhere is a good approximation to the ground state, right?
Depends on which Hamiltonian, right? So the question is, what is your Hamiltonian? There is an ideal Hamiltonian that makes that question always the answer being yes. But it's
So
kind of like
even
reverse engineering, right? So, but if you take Coulomb, right? If you just take like the Coulomb Hamiltonian and you solve it in the lowest Landau level, typically, by 1/7 or 1/9, the ground state already crystallizes. So that tells you that Laughlin wave function stops being a good approximation to the true ground state of Coulomb. So it depends on which microscopic Hamiltonian you have in mind. But there is one Hamiltonian you can write down by hand for which you guarantee that the Laughlin wave function is always the ground state.
I'm kind of more interested when you go down.
Even when you go down, the wave function, all you have to do, the same Hamiltonian that you write down in the lowest Landau level, you just have to, what you do there is you project it to the lowest Landau level. All you have to do is project it to the new band and it's still exact because all that Hamiltonian is doing is guaranteeing the short distance vanishing of the wave function when particles approach. And we're keeping that exactly the same. The wave function has the same order zeros. So all the short distance properties are enforced by the Hamiltonian and it's exact. So you can write down the same Hamiltonian just projected to this new band.
Right. And the model has broken explicitly both translation and rotation because of this, right? Because
exactly. So translations are broken explicitly by this solenoid lattice, and rotations become some kind of discretes, of the lattice.
Right.
And so that's the point that makes it weird, that we're not, there is some gaplessness even though we're breaking translations explicitly. It's not the spontaneous symmetry breaking.
Rotations, you have like some kind of discrete subgroup.
There is a discrete subgroup, yeah.
Rotation.
Yeah, I think it's very non-trivial what is going on. I think it has to do with a kind of, basically some modes remain soft and they probably have to do with some kind of inversion symmetry breaking of the Laughlin state. So I have a gut feeling this part is still not very well developed. But this phase is separating two phases of matter that have to do with spontaneous inversion symmetry breaking. So some kind of like Laughlin ferroelectric states. And this is critical. Yeah. Spontaneously breaking when you go, like when you add another axis here. And this is like the critical phase separating all the broken symmetry states. Maybe inversion is like relevant for that, I feel. But that part is still like kind of in the air. Yeah.
If there is no more questions, thanks the speaker one more time.